Thank you very much to coming to participate the 18th Science in Japan Forum.
For environmental issues such as preventing global warming, we have had in Japan the so-called earthquake, which involved the nuclear power plant problems, and the energy problem is an urgent issue for Japan, but not for only Japan, but also for probably the United States and all over the world.
One of our two nations' most fruitful research collaborations focuses on a goal of this meeting, and this is encouraging international collaborations in chemistry, for after all, chemistry can save the earth.
International engagements recognized through forums like this help ensure that we discuss and come to share the awareness of the research priorities and the directions around the world, especially the values shared by Japan and the United States.
I hope this forum will create a momentum for such cooperation, especially for artificial photosynthesis.
Well, chemistry, yes, works to save the earth, but I'm going to remind you for just these 3 minutes that I'm allowed that chemistry also works to save lives. And that, of course, is what we do at the NIH and what you do in Japan.
Education is lagging among fundamental researchers and general society, including companies and the government scientific strategic policies. Okay. So from that meaning, I hope we will be able to have a concrete grip on the future prospect of artificial photosynthesis.
My first talk will focus on addressing the great transformation emerging around the world. I would like to start by stating that the great transformation takes place around the world. We're facing the multiple challenges.
If we make very flat electrode surface, the stability is much worse. And I consider that the lower current density seems to be better to stabilize this kind of material.
Our job is to give the world something it doesn't now have. It simply doesn't have a good way to convert the biggest energy source we have into the most energy dense form of storage other than the nucleus of an atom known to mankind, which is chemical fuels.
But what I have been emphasizing here and there and everywhere is the significance of D block transition metal as a catalyst. D block transition metals as catalyst. The more we use, I think, the better off we will be. And that is, I would like to present that as the single most important message in my talk today.
They're big complexes, 14 atoms across. They have a very low affinity to each other. These surfaces tend to load in monolayer coverages. They line up. And they really do. You can tell that. I mean, we can't do a structure on the surface, but we can look at loading isotherms. So that part's actually well behaved, without significant complications. Although it is important that cross-surface electron transfers are there, and we take advantage of them.
And Cox cycle state is S1, but that S1 is expected, but I feel in real state is a little bit reduced, maybe around S0 or S-1.
You know, the model that we all are using is natural photosynthesis, and of course, as has already been pointed out, nature's been doing this for more than 3 billion years, and as a consequence, it is essential for us to understand just how this process works at the molecular level. And indeed, that's what's in fact happened over the last 30 years or so.
And probably the charge separation, the pantaloxy nitrate, was improved by addition to the silver. Or probably the electron is pulled
on the silver and easily transfer to the metal complex. We don't know the real reason in this point. So it's a very important point.
At 1.03, so I can't oxidize water, I can make cobalt oxocubanes, and I find out when they're reduced, and I look at the catalyst looks like cobalt-2. So it sits in a resting state of cobalt-2. You then oxidize it to cobalt-3, can't see that by EPR, but we can see by Zanes.